everybody. Hi. So my name's Charlotte. I'm a PhD student in my 4th year now. So I don't know if anyone knows what that means, but I'm stressed. Very, very, very stressed. So is anyone else in here a scientist?
Yeah.
Hands up if you're a scientist. Or shout. Are we that kind of crowd? Shout if you're a scientist.
Yeah.
Yeah, it's great, isn't it? Oh, shit. So anyway, does anyone know what this is a picture of up here? Anyone got any ideas? Species? Slabs? Species? Anyone?
Fish.
It's not fish. It's actually yeast. Yeast. This is a yeast cell. And this purple blob inside it is its DNA. And here it's actually growing through the cell cycle. So this is the process where it basically replicates its DNA, so it's got twice as much DNA as it did before, and it stuffs half of that DNA into the new baby cell, and voila, you have 2 new cells. So, I can hear what you're asking. Why on earth are you studying yeast for your PhD? That's ridiculous, right?
That's ridiculous.
No! It's because they are so similar to us. And if I stand here and you look at us, you can see that we are virtually indistinguishable. We are so similar. Actually, the only bit of an organism that I'm ever interested in is what's inside the nucleus. So, you know, everything to me is the same. Mouse, same as a dinosaur, don't care. The nucleus, the same thing going on. So if we dive into this nucleus, that's where I'm focusing, that's where I'm concentrated. And the processes I study inside the nucleus of a yeast are so incredibly conserved throughout all of life. So that's why we can learn about us from studying yeast. And the processes that I study are DNA damage repair and also genome organization. So it might shock you to know that there are actually tens of thousands of lesions, of breaks in your DNA every single day. So every single one of your cells, tens of thousands of breaks. So your DNA, broken. Now, if your cell does not repair these breaks, it is one thing, my friend, and that is fucked. Okay? It has to repair it. If your cell does not repair its DNA, it's a bit like an overfed pigeon that is useless, unable to reproduce, and liable to explode. So it's really important that it does repair it. So how does a cell do this? And I thought, this is actually something that I struggled to explain to myself ever, and I've been studying it for 4 years. So I thought I'd, type it into Google, see if I could think of a way to explain it to you guys, and this is what came up. Yeah. So, there was a time where I'd look at this kind of thing and be like, I'm going to memorize the whole thing, every single tiny little thing, I'm going to memorize every single one of these proteins. But now I'm like, no, I want to know actually what's going on inside the cell. How does a cell actually repair its DNA? If you miniaturize your head and stuff it inside of a cell, this is not what you see happening inside the cell. Right? Something different. How does it get these 2 broken bits of DNA and physically stick them back together? Now, to illustrate this, I'm going to tell you a bit about how the DNA actually looks inside the nucleus, and I'm going to use a metaphor to do that, because your DNA, when you imagine it, you might be thinking of a long strand, a long straight strand. That's not what it's like at all. So I'm going to use a metaphor. So I don't know if any of you are old enough to remember this, but there used to be like a phone that you had in your house. And it was physically attached to the house, okay? So you had a phone, you hold it, and then a wire came out of that and it went into the house. Pretty weird, eh? So anyway, when you're on the phone to Jane, you're like, oh, hey Jane, how's everything going? Oh, I know, right, it's really hard. So what you were actually doing is you wasn't actually listening to Jane. What you're doing is you were coiling that coil up. You were coiling it, and you're recoiling it, and you're coiling the coil, and this was very exciting for some reason. And you know what? That's exactly how the DNA in your cell is. It's coiled, and it's recoiled, and it's coiled again. It's under tension. It's not in a hairball, it's not in a straight line. It's in this incredibly, amazingly coiled fashion. And it's like a little jungle in there with loads of other things stuck to it. So, let's say your son walks into the room. You're like, all right, Jeffrey, what are you doing? I'm on the phone to Jane, you're piss off. Anyway, but then you realise he's got a pair of scissors. You're like, okay, what's he going to do with that? And he runs up and he cuts the telephone wire. And what happens? What happens to the telephone wire? It's under tension, it's coiled and recoiled. What happens is that the wires, they spring apart and they spin off into different areas to the different sides of the cell if they're pieces of DNA. So what do I actually think of when I think of DNA that's been cut like this? I don't think of this diagram. I think of wacky waving flavour one flailing tube man. That's what I think of. Because these two pieces of DNA flail away from each other. And how on earth is the cell going to be able to bring those two flailing bits of DNA into the right position and fix them back together again? Well, let's carry on with wacky waving flavour one flailing tube man as another metaphor, digging our way into metaphors here. So what would you do if you wanted to join those two waving arms back together again? Again, I know what you're thinking. You would get a system of very sticky donuts. You would thread them onto his arms, and that would give rise to a Rad51 filament, which is recombination competent. That is what you're all thinking. That is exactly what happens. Crazy this. So, okay, let's explain this diagram a little bit. So this is the end of your piece of DNA. There's just been snipped, you've had a break in your DNA, which is shit, and the cell needs to fix it. And what happens is this amazing protein, Rad51, binds along the length of the broken piece of DNA. And that enables the DNA to be able to search the whole of your genome, and the genome's big. This is an amazing process. It searches the whole of the genome, wiggles around, and it finds, like a snake swimming through the ocean, it finds exactly where it needs to be able to repair your DNA. It invades the other strand, the sister strand, and uses this as a template for repair. It's pretty amazing. And it gets a little bit more complicated, but we won't talk about that bit. So just remember, now and every day, your DNA is repairing itself, and it's pretty amazing. Thanks for listening. I'm Charlotte Mykura.